Welcome to this session. This session, we are going to discuss how to solve differential equations using matrix method. So whether you are given a system of linear differential equations or if you are given a higher order linear differential equation, how you can use matrix to solve the given system of differential equations or the given higher order differential equation. So we start by describing how the solution is obtained. So let's see the workings. So the method of eigenvalues and eigenvectors. So as far as the solution of the equation, x dot equals to ax are connected or are concerned. So as far as the solutions of the form x dot equals to x are concerned, the analogy is for this given equation, x dot equals to x, where a is a constant. And of course, a non-zero constant. And this equation gives rise the exponential should also satisfy you say for this now, remember dot means this notation. When I write x dot, I mean derivative of the vector x with respect to time. When we write x dot, we mean dx dt. So dot means a derivative. If there are two dots, then to be second derivative, three dots, third derivative, etc. So the solution of this differential equation, we know that the solution to the differential equation x dot equals to ax is x of t is given by x naught e raised power at. So in the case of this vector notation of this equation, x dot equals to ax, where a is a matrix, then we pick the same analogy of the structure of the solution. So we say, let us assume for this given equation that the value of x of t is given by a vector u times e raised power lambda t u is the eigenvector and lambda the eigenvalue for the matrix A. So I assume that the structure of the solution of this vector is the same as the structure of this simple first order differential equation, where the x naught is replaced by the u vector, and then this is the scalar lambda, which is eigenvalue, and this is the normal t. So x dot is given by, so differentiating this with respect to time, simply use chain rule, will have lambda u vector e raised power lambda t. So since then x dot equals to ax becomes, so where this x dot, you replace by this value, so lambda u e raised power lambda t is equals to a, and where this x, we have said the solution to be u e raised power lambda t. And then this can be written as, bring this to the other side, so we'll have a u e raised power lambda t minus, now because this is a matrix, so for us to take all these terms to one side, then we have to introduce an identity matrix of the same order as A to this term. So lambda I u e raised power lambda t should give us a 0 vector, because now this will be purely vectors. So in these two terms, u e raised power lambda t is common, so you can say A minus lambda I, and then I multiply by e raised power lambda t, and then times the vector u is given by 0 vector, i.e. A minus lambda I times the vector u should give us a 0 vector, since we know that exponential can never be 0. So, and we say from this equation, this is actually the relationship between the eigenvalues and eigenvectors of a matrix A. So if we call this one equation 1, so we see that question 1 is the expression, or is the equation that precisely gives the connection between an eigenvalue lambda of a matrix A and the associated but it's not there, and the associated eigenvector. Eigenvector U. So therefore, whenever lambda is an eigenvalue of A and its corresponding eigenvector U exists, then the solution of the equation x dot given by Ax is x of t given by U e raised power lambda t. So that is in general. We can put it in a theorem and say if U is a real eigenvector of A. Now, when you say real eigenvector, we mean that all the components of the vector U1 are real numbers. Corresponding to the eigenvalue lambda 1, then x1 of t given by U1 e raised power lambda 1 t is a solution of the equation x dot is given by, remember there's an arrow here to show it's a vector, x dot is given by Ax for all values of t. So that's what we have, that if you have an eigenvector corresponding to an eigenvalue, then it is always a solution to any equation of the form x dot equals to Ax for all values of t, where t the variable independent variable. Theorem, that's called the superposition principle. So the superposition principle helps us to give the general solution of a given equation of the form x dot equals to Ax, which has some sub-solutions. So combining, getting the linear combinations of all the solutions gives the general solution of that, or to that given equation. So you say, assume that x1 of t, x2 of t, x3 of t, up to xn of t are solutions of this equation x dot given by Ax. Then the general solution to this equation x dot equals to Ax is the linear combination of x1, x2, x3 up to xn. Of course, these are functions of time, functions of time, functions of time, functions of time, i.e. x of t is given by c1 x1 of t plus c2 x2 of t plus c3 x3 of t up to plus cn xn of t. So whenever you get the linear combination of all the solutions of the given system or equation x dot equals to ax, then this is the general solution. So where C1, C2, C3 up to Cn, all of them are real numbers. So this is how we find a general solution to the equation x dot equals to ax. So assuming that the value of lambda is a complex number and the value of the eigenvector u is also complex. So when lambda is given as a plus bi and u is given by v plus w, then the solution to the equation x dot given by ax remains to be x of t is given by u e raised to power lambda t, i.e. we'll have u which is given by v plus w, iw, and then e raised to power, where there's lambda, I put a plus bi, and then I multiply by t. So this can be written as e raised to power at plus bti times v plus iw. I've just rearranged the terms. And then loss of indices, this can be written as e raised to power at, e raised to power bti into v plus iw. But you see from Euler's identity, e raised to power theta I is given by cosine of theta plus I sine theta. So we can derive this term as, so x of t will be e raised to power at, and then instead of writing this one, we'll have now cosine of bt plus I sine bt, I multiply by v plus iw vector, where theta in this case is taken to be now bt, relating the Euler's identity and this term here. So then let's carry out this multiplication. So we'll have e raised to power at. This by this will have v cosine of bt. This by this will be plus iw cosine of bt. this by this will be plus v I v sine of beta t, bt. I times I is I squared, which is -1. So we'll have W sine bt. So what we do, we collect real parts and imaginary parts. So this will be e raised power at. So this is v cosine of bt, and then minus W sine bt plus, so I factor out I. So this will be v sine bt plus W cosine of bt. So therefore, this is the x value. And then multiplying every term by e raised power at, we have e raised power at into v cosine of bt minus W sine of bt plus I e raised power at into v sine bt plus W cosine of bt. So therefore, we call this one x1. When you are dealing with complex case, this part, you call it x1, and this other part, you call it x2. So by superposition principle, the solution is x of t will be given by c1 x1. Actually, you can say x1 of t, x2 of t, or there are two of them, x1 of t plus c2 x2 of t. So hence, when lambda is equals to a, it can actually be plus or minus bi, and u, the eigenvector, is given by v plus wi, then the general solution to the equation x dot given by ax is given by is x of t equals to c1 x1 of t plus c2 x2 of t, where x1 of t is given by e raised power at into v cos bt minus W sine bt, and x2 is given by x2 of t is e raised power at v sine of bt plus W cosine of bt. So this is how we find the solution in case we have complex eigenvalues and eigenvectors for A matrix. So I'll do an example to illustrate that one in the next sessions. Thank you.